So here's the actual definition of Coco values that we're going to use and that come from the Collide work. So the Coco value of a game is going to be defined like this. Let's imagine that we've got a general sum game. The notation I'm going to use is U is payoff to you.
Okay.
And U bar is the payoffs to not you, right, the other person.
Yeah, that makes sense. Okay. Although I like that you use the bar because that means compliment. So you're saying we compliment each other.
This has nothing to do with me.
You said you.
It has something to do with you.
Okay, now you're just confusing me with your pronouns.
All right, sorry. So I should have called the other matrix I. No, wait, that's not going to help. All right, so so the general sum game that we're actually solving here is U bar. And why don't we just compute, say, a Nash equilibrium of that general sum game? Well, there's a bunch of reasons. One is that they're hard to compute. Another is that maybe it would be indifferent to getting those extra bananas and sharing them around.
Right.
So what we're going to do is we're going to define the Coco value, and we're going to use the Coco value to actually divide the spoils. So here's how the Coco value is defined. We're going to take the general sum game U bar, and we're going to turn it into sort of redistribute all those utilities that are in those two matrices to create two matrices, one that's purely cooperative and one that's purely competitive. We're gonna create one game by thinking about the average values that the two of us would get for each of the different possible joint actions.
Sure.
Right. So imagine that we'll get whatever we get and then we split it evenly.
Okay.
All right. That's very cooperative.
That is very cooperative.
And in fact, mathematically, it's just U plus U bar over 2. It becomes the matrix payoff that we're both going to abide by.
That seems reasonable.
Purely competitive version is for us to look at the difference between the utilities that we get and split that in half. Right. So it ought to be the case that if we add these two matrices together, U plus U bar over 2 and U minus U bar over 2, we get U from my perspective, from U's perspective, and we get U bar from the perspective of the other player. So we recover those same utilities from the general sum game, but we've redistributed them into these two matrices, one of which is purely cooperative. We get the same payoffs, and the other one is purely competitive because one of us is playing U minus U bar over 2, and the other is playing the negation of that, which is U bar minus U over 2. Right, so what's good for you is bad for the other player, and vice versa.
Okay.
In particular, this is a zero-sum game now.
Right. So in fact, I was actually going to ask, what would happen if you were playing a zero-sum game? Then U plus U bar would always be 0, and in fact, this would say you should do minimax on the gap.
U plus U bar would always be 0. Yeah. Once we've redistributed these into a new U and U bar, yes. And so what's the Nash-like thing, what's the equilibrium-like thing to do when we're playing a purely competitive game, and that's to take minimax. So we're actually going to compute the minimax value of that game, and we're going to compute the maximax value. In other words, which cell has the highest sum payoff or average. You say sum and average is the same. Find the cell that has the largest thing and say, okay, well that is also a Nash equilibrium of the purely cooperative game. Because if we choose the square that has the highest payoff out of everything, then we're going to have no incentive to switch to something else.
That's right.
How do we compute the cooperative equilibrium?
You just replace all the things with their sum and take the biggest one.
So it's like taking a max of all the cells of the matrix.
A max of all the of the new cells of the matrix.
Of the new matrix, that's right.
That's right.
And what about minimax?
Wait.
Do you not remember how to do that?
No, I do. I try to remember which one is which. Let's pretend I don't remember how to do it.
Anything that's not a dynamic program is a linear program.
Truer words have never been spoken.
Because it's all about programming. All right, so in particular, you can set this problem up as a linear program and solve it in polynomial time. So this is efficient, at least in a formal mathematical computer sciencey kind of sense. And so is this.
Right.
So we took a game that we actually don't know how to solve because computing a Nash equilibrium can be really hard. And we've broken it up into two, again, just by redistributing the wealth, redistributing the utilities, we actually split it up into two games that are the same amount of utilities being spread around, but we can actually compute the equilibrium value for both of them really easily, and then we're just going to add them together.
Okay. And then what does that tell us to do?
Good question.